Okay, last time we got into really measurements, significant figures. Remember we talked about sort of the rules there for sig figs. That being obviously that all non-zero numbers are significant. We then have our zeros and our three types of zeros. We have our leading zeros, which are not significant. And those again are all the zeros that come before you hit that first non-zero number. They are not going to be significant. We have our trapped zeros, which are significant. And those again are basically zeros that are trapped between two non-zero numbers. Then we have our trailing zeros, which are going to be significant if there is a decimal point. So if we had something like this, these zeros at the end would be significant again because of the decimal point that's there. Remember that really significant figures come from measured numbers. And these are really, in most cases from some type of measured number. There's also exact numbers that we talked a little bit about as well. Exact numbers, again, are definitions, like 12 inches equals 1 foot. There's something that is counted. In terms of significant figures, anything that's an exact number can really have an unlimited number of significant figures. So as we will talk about when we do calculations, we really don't look at exact numbers to help us determine how many significant figures our answer should have. We really only look at the significant figures in sort of like the measured type numbers to help us make that decision. Again, because exact numbers pretty much can have an unlimited number of significant figures. We finished up, I believe, talking about calculations with significant figures. And remember that if you sort of multiply or divide, you are looking at significant figures, and it is the least number of significant figures. So if you do any type of multiplying or dividing in terms of the math in a problem, your answer should have the same number of significant figures as whichever number has the least number of significant figures. Remember, though, if you're doing some addition or subtraction, it's a little bit different. We're looking at the decimal places, and it also is the least. So your answer should have the same number of decimal places as the one that has the least number of decimal places. Remember that, as we talked about, if you're sort of doing a bunch of calculations in a row, you really don't want to round, but you do want to also kind of keep track of everything that you did in terms of, did you multiply, did you divide, were you adding, were you subtracting? And then you really want to kind of clean it up at the end, really based on sort of the last calculation that you do will really kind of determine, where your answer will end up, especially if you're doing multiple sort of calculations together. But it is important, as I think we talked about as well, not to do too much rounding along the way. But you definitely should keep track of really where everything should end up. Any questions on any of that stuff there? All right, then let us continue on. So when we look at this here, take a moment here, and once you give what each of these answers should round off to. Again, if you did these math, again, your calculator will not necessarily give you the correct number of significant figures. So what should each of these end up being? So take a moment and make sure. Okay, so let's take a look at each of these. So obviously here, first off, we are multiplying. So it is significant figures we want to look at. First number's got 3. Second one's got 2, which means our answer should end up at 2 significant figures, which if we start counting, pops us there to the 3. We do have to look at the 7, which means we do need to round up in this case, and we should end up at 9.4 as our answer. Any questions on that one there? Same thing here on the second one, we're dividing. So again, we're going to look at significant figures. We got 4 significant figures on the first one. We got 3 on the second. So again, we should end up with 3, which is the least. Remember, we're not going to start counting until we hit the 7. That means our third significant figure there is actually the 8 in this case, and we should end up with this as the next number is a 2, so we could just drop the rest of them. Coming down to the next one, we're actually adding in this case, which means we're not looking at significant figures here, but we're actually looking at decimal places. So that is a couple decimal places. That's 1 decimal place, and that is 3 decimal places. In this case, we actually should end up at 1 decimal place. Looking at the one next to it, which is a 3, we will end up with 29.1 in this case. And lastly, we're subtracting, so same thing, decimal places. That's 4. That is 1, which means we should end up here at the first decimal place. We do have to look at the 8, which obviously is above 5. So we do have to do some rounding upwards there to 0.6. Any questions on any of those there? So again, calculator obviously will not give you necessarily the right significant figures. You got to kind of clean it up at the end of the calculation. All right, so we talked a little bit about this previously, but just again to reiterate, you do need to know how to use these correctly. You do need to know, I would say probably this table right here, all of them are ones that you'll use a lot in chemistry. And here for sure, we'll see kilo, centi, milli. Again, as you go to 1A, nano, you'll see micro probably a lot, and you'll see mega a lot. But those big three we definitely will use a lot in here, but they do want you to know these type of things. So a reminder that when we use these prefixes to sort of change the meaning of a number, you want to make sure that you do use it correctly. And basically this right here is, again, how much there is in the base unit to one of the prefix units. So again, if we look at mega, which is 10 to the 6, and by the way, 10 to the 6 is scientific notation for 1 times 10 to the 6. If you need to punch into your calculator, again, you would punch it in like we talked about using your exponent button, and that's how you would punch it in. What that means is, for example, if I had 1 megagram, there would be 10 to the 6 grams. So again, in the prefix unit, which is this one of those, that is how much there is in the base unit here. And again, you want to make sure that you do that correctly. Same thing if we had centi, 10 to the minus 2. That means in one of the prefix units, like 1 centimeter, there is 10 to the minus 2 meters. So again, people always want to kind of do it the opposite way and go, again, something like 10 to the minus 2 centimeters is 1 meter, and kind of do it backwards. And you don't want to do that. You can, I think, as we also talked about, get sort of the larger number if you divide that to both sides. And again, that would give you sort of the larger version of that, which is 1 meter is 100 centimeters, if you kind of did that. So that too is a conversion that you sometimes will see. It is the same conversion. It's just sort of looking at how many centimeters there are in a meter rather than how many meters there are in a centimeter. So it's just sort of the opposite of that. Any questions on that there? Yeah. So definitely make sure you probably know everybody on this table is probably a good one. And more importantly, know how to sort of use it correctly and not sort of get it backwards. So again, some of our common length equalities. A reminder that an equality is, again, 2 values on different units, but they do represent the same amount, or whatever you're talking about, our same distance. So 1 meter is 100 centimeters. Again, that is something we use a lot. 1,000 millimeters in a meter and 10 millimeters in a centimeter. Again, that's what you see on the bottom of the ruler, where you have centimeters and all the little dots that go into it. Those are millimeters. Again, there's 10 of them going into there. Volume 1 liters of 10 deciliters. This is definitely, in terms of volume, again, one that we use all the time. So probably one of the most common volume conversions that you do in chemistry is that, and definitely you should know that for sure. It is your milli sort of prefix, but you definitely should know that one. Obviously, I think we touched upon this as well. There are a couple of different sort of volume measurements that might not seem like volume measurements, but again, like you're going to do in lab today, if you take the length times the width times the height or something like a cube, and you measure it all in length measurements of centimeters, you will get again a cubic centimeter, which is a volume. Again, each of these individual centimeter measurements are length measurements, and 1 cubic centimeter equals 1 milliliter. That is also obviously definitely something you should know. A cc is also an abbreviation for a cubic centimeter. It's usually used in like medicine when they like give you a shot or something like that, give you 4 cc's of something. They're basically just giving you 4 milliliters of it. And that's used a lot in sort of medicine. But 1 cubic centimeter is equal to 1 milliliter is definitely something that we do use a lot. The good news is it's really a one-to-one conversion, which means no numbers change, just the units change basically. The difference between that a lot of times is when we see density, for example, for solids, sometimes we'll do it in grams per cubic centimeter versus say a liquid, we'll do the density units in grams per milliliter, but it's basically the same number. All right. So again, if you see a centimeter, we're talking about length. Cubic centimeters are really any sort of length measurement that is being cubed, like decimeters cubed or things like that. They're really talking again about a volume. That obviously is a graduated cylinder, which on this particular scale, that is 70, that is 80, that is a 10 milliliter jump. And there is 1, 2, 3, 4, 5. On the smaller markings, again, in this case, each of the smaller markings is going to be 2 milliliters. So this again would be a graduated cylinder where the best we could do is a whole number on this one, right? As we divide our smallest marking by 2, gives us plus or minus 1 milliliter in this case, right? If we did have a volume in this particular graduated cylinder. Obviously, these are some important mass equalities. 1 kilogram is 1,000 grams, used a lot, and also grams to milligrams is used a lot. I don't think you hit too much micrograms, which is what the last one on the right there is. That's micrograms. We probably won't see too much of that, and probably truthfully, you won't see too much of it as you go through your other ones as well. But definitely those two, you definitely should know these guys. All right. So let's take a look at some of these. Again, 1 kilogram is 1,000 grams. 1 milliliter is 0.001 liters. And again, that is our milli conversion. And our milli being, as we look at that table, basically 10 to the minus 3. That is, again, 1 times 10 to the minus 3. And that is, if you turn it into a decimal, 0.001. Again, plus you 1, 2, 3, basically, yeah. All right, so let's talk a little bit about writing conversion factors. And the idea, what we're going to talk about now, is really how they want you to kind of show your work when you show work in chemistry. And it really is, as we'll see, what is referred to as sort of dimensional analysis. And really, conversion factors is a really important part of sort of how we show work. So, for example, the idea of dimensional analysis is this. You have different units, and we set up the calculation so that we could see the units, and we cancel out the units that we don't want, and we keep basically the units that we do want. And to do that, it's really opposite. So, for example, if we had like unit A, and we want to kind of get it into unit B, for example. And maybe we have some type of relationship between those two that for every 2 of unit A, there's 4 of unit B, right? So if we had, say, 6 of the first unit there, and we wanted to figure out how much of the B units that would be, we would set this up going with 6 units of A, unit A. Now we actually need a conversion factor, and this right here in this example would be an equality. And really from any equality that you have, you can write two conversion factors, and they're basically just fractions. So I could say in this case 2 of unit A over 4 of unit B, or the other conversion factor is basically just the reverse of that, 4 of unit B over 2 of unit A. So these are the two sort of conversion factors I could get from this equality. Now, will you use all the conversion factors in your calculation? The answer is no. Otherwise, you're probably going to do your calculation. You're just going to use the one that you need. So when we set up dimensional analysis, which is how you need to kind of set up your work, as I mentioned, you do need to do it like I have there. And you want to think of it really as just a fraction and don't overcomplicate it. Opposites cancel out the units. So although 6 unit A's here is not really written as a fraction, you can kind of think of it as being over 1. And that means that when we think about unit A, it's up on top. And to get rid of it, we need to put it in the opposite location, which means we need unit A on the bottom. And that would be in my example here, this conversion factor, which has unit A on the bottom. And we would use that as our conversion factor to do this calculation. Now, unit A on top, when you divide it by what's on the bottom there, that's going to cancel out. And mathematically, what we're doing here is whatever's on top gets multiplied, whatever's on the bottom gets divided, basically. So we're essentially dividing unit A divided by unit A. It is kind of the same idea. Equals 1. If you divide like 2 divided by 2 equals 1, they're basically the same on top and bottom. They cancel each other out. So this is the way that you should show your work here. And in this case, what we would do is multiply the 6 times the 4, which gives us 24. We then divide it obviously by 2 on the bottom there. That is going to give us 12. And the units that are left over in this point is unit B. So we just sort of did our little dimensional analysis. So conversion factors are really obviously important in these type of calculations. They are really what we use to get rid of units that we don't want so that we can end up with units that we do want. The nice thing about setting it up like this is in a lot of cases, even if you maybe are not sure of the formula that you should be using, and you could just kind of get rid of the units you know you don't need and end up with the units that you do need. You could almost kind of do the calculation without maybe knowing the formula correctly, and you could kind of just get out the units that you need, and it'll kind of do it for you, the formula. So it's really the way that you do need to kind of show this. Any questions on that there? Yeah. Now, again, from any sort of equality, we could write two conversion factors. And again, those equalities mean the same amount of something. So if I had $1, that is the same as having 100 pennies, and that would be our equality here. And again, the two conversion factors I could get is 100 pennies up on top divided by $1. Or I could flip it around, $1 over 100 pennies. Now, if I had something like I had $22, right, and I want to know how many pennies that would be, I could set up my problem here with dimensional analysis. Again, the dollars are basically on top. That means I need to go opposite to cancel it, and that puts dollars on the bottom so that those units cancel. Our dollar will cancel here. We again are going to multiply what's on top and divide by what's on the bottom. In this particular case, obviously, we don't really need to divide because there's only 1 on the bottom, so it's not going to really change. You can divide it if you really want. And we'll end up with 2,200 pennies in this case, yeah. Now, if you are looking to solve for a particular unit, one unit by itself, the unit that you want to solve for has to be on top, right? So if you have like one unit that you want to end up with, it's always got to be on top. If the unit's on the bottom and you solve for it, you're not really solving for that unit, right? You're solving for the reciprocal of that unit, 1 over that unit, right? So you would actually have to do that math to get the right answer. So whatever unit you're trying to end with, that is what should always end up on top by itself. Like here, we wanted to end with pennies. That's up on top by itself. Now, if you did have, for example, come back here and look at something. Let's just say we had, you know, 200, we'll do 222 feet per minute, right? And we want to know, for example, how much miles per hour that is. In this particular case, we actually have 2 units, right? One on top, one on the bottom, and we do need to do conversions for both of them. By the way, when you do have units like this, where you have 2 units, typically the number stays with the top unit, and the bottom is usually like 1 of the bottom unit, and that's usually how you kind of keep that. So we could use some conversion factors that would help us. For example, you could find, or you might want to know, that there's 5,280 feet in 1 mile, for example. And again, that's going to be our equality here. And from that equality, we could get 2 conversion factors, 5,280 feet over 1 mile. Our 1 mile is 5,280 feet. We also need some minutes to hours. So there are, I believe, still 60 minutes in 1 hour. And obviously, this is our conversion factors here. And that also gives us, from this equality, 2 conversion factors that we could have: 60 minutes over 1 hour. Our 1 hour is 60 minutes. So it's important when we kind of set up this problem that we really do set it up dimensional analysis, that we could clearly see where all the units are. So when we start with this, I'm going to start with what was given, which was 222 feet over a minute. And again, I'm going to clearly have like a top and bottom type situation here. That way I could clearly know where the units are. When people do not set these things up using dimensional analysis, besides the fact that they expect you to do that in chemistry here, a lot of times what happens when they kind of not very careful with the units is just kind of write it out. At some point, people kind of lose track of, where is that unit? Is it on top? Is it on the bottom? And that's really important, because what they lose track of is, should I multiply? Should I divide? They'd kind of do the wrong math part of it. So if you keep all these units really clearly, like this is on top, this is on the bottom, it almost becomes like a no-brainer of what you need to do mathematically, because when you do dimensional analysis, there's really only 2 types of calculations you're doing. You're either multiplying or dividing. So if it's on top, you're going to multiply. If it's on the bottom, you're going to divide. So if you keep everything separated like that, you don't have to think about, should I be multiplying here? Should I be dividing? It'll kind of do it for you. So in this case, we basically just got to do this conversion and this conversion. It really doesn't matter which one you start with. I'm going to start with the top. So up on top, I do have feet, which means I want to get rid of feet. So I'm going to go opposite of the top where feet are, and I'm going to use the conversion factor here on the right to do that. And that will give me 1 mile on top and 5,280 feet on the bottom. If I do the calculation at this point, I could get an answer, but I'm not going to at this point. But in terms of units, the feet at this point will cancel out. If I stop my calculation right at this point, I'm in units of miles on top per minute, basically. Yeah, so miles per minute. So we got the top part good. So now we need to get the bottom part, which is we need to get the bottom from minutes to hours. Now, because of the way I wrote it, there should be no misunderstanding of where those minutes are. They are on the bottom, which means to properly get rid of them, they need to go in the opposite location, which means they need to go up on top. And that is the conversion factor that I need to use. And we can continue our calculation here with 60 minutes on top and 1 hour on the bottom. Minutes divided by minutes cancel each other out. Now I have miles per hour as my units in this case. First off, any questions on that setup there? Can't tell you how many people will probably do this problem and not multiply the 60, but divide the 60 and do it incorrectly because they're not keeping track of where the units are. So it's really important to keep the top, the bottom, so that you get all that correctly. Now, again, mathematically, we're going to take whatever's on top, all that's just getting multiplied, and whatever's on the bottom, we're going to divide. So it's basically just those two operations. Now, when you do problems like this, I highly recommend you do this. You take whatever numbers you have on top and you can multiply as many numbers as you like up on top. Once you get to the very last number up on top, use your calculator, hit equals, hit your equals button. And then you should come back and divide by whatever's on the bottom. And my recommendation is if you have multiple numbers on the bottom to divide by, I would divide by each of them individually. So people oftentimes make a calculator mistake when they try to punch like everything in at once onto their calculator and they end up getting the wrong answer. So for example, in this case, we only really have one number. So we're going to divide by 5,280. And we're going to end up with here 2.5 and 227, 2272. That's good enough here. 7273. The units are miles over hours in this case. Now, in this case, if we did have another number on the bottom, I would hit divide by 5,280, hit equals, divide by the next number, hit equals, divide by the next number, hit equals. So don't be afraid to divide by each number individual on the bottom and use that equal sign in between each one. And you'll always get the right answer if you punch it in that way. If you try to punch it all in at once and you do it correctly by using parentheses correctly, you will get the wrong answer. First off, any question on the calculation? Clearly, that's way too many numbers for our answer. Yeah, so we do need to clean it up. So here's where we want to look at what we're dealing with, right? So this is obviously an exact number, an exact conversion, which means it has a limited number of significant figures, which means you really don't have to sort of worry about it. If you're dealing with anything that is a English to English conversion, a metric to metric conversion, they're considered exact numbers and you really don't have to worry about them in terms of your calculation. It is only when you kind of cross over metric to English that you do have to worry about the significant figures, except for a few that we talked about, I think, earlier on in this chapter that are exact conversions, like 1 inch is 2.54 centimeters, those type of guys you don't have to worry about. So we really don't have to worry about this one either. That's like English to English, right? There's no meters or anything in that one, which means in terms of significant figures, that's really the only thing we got going on in terms of what we do need to worry about. So that is 3 significant figures. As I mentioned before, the good news about dimensional analysis is all you do is multiply and divide, which means you're always looking at significant figures pretty much when you set it up like this. So our answer should end up at 3, which is right about there, I think. So we really should take this guy and write the right number there, miles per hour in this case. Any questions on that? So it's really important that you set up all your work this way through dimensional analysis. When they say show it through dimensional analysis, that is what they're looking for, using conversion factors, setting up the calculation. Now, do you have to write all the equalities? You have to write all the conversion factors out when you're doing a problem? The answer is no, you don't. But if you want full credit on any type of calculation that you do that is dimensional analysis based, you pretty much need to show the setup like this, where you can see all the units and the conversion factors that you did use and canceling out. And obviously, correct answer there is a significant figure with the units. So for credit, full credit, that's what you need to show. If it helps you to write out the conversion factors and the equalities, go for it. But you don't have to show all that rest of the work. It's actually 3 significant figures because we're actually only looking at, in this particular example, this is really the only number, the first number. that we have to look at, because these are kind of considered exact numbers, the two conversion factors that we use, because they're basically exact conversions, right? So that really defaults back to the first one. So I will say probably in most cases, and again, that obviously has 3, which is why we end up with 3. In most cases, 90, I don't know, 98, 99% of the time, if you're doing some type of problem like this, probably that very first number that you got going on is probably going to be pretty much like the right number of significant figures. I won't say 100% of the time, but it's probably pretty high 90s type of situation that if you kind of roll with the first numbers, significant figures in a calculation like this, you probably will be either correct or super close to the right one. Now, the exception to that is if we have a metric to English type conversion that kind of slips in there, that we have to kind of take into account the significant figures of the conversion factor. But in a lot of cases, even the conversion factor, that if you do have to look at the significant figures, a lot of times is still more than the original number a lot of times. So not always, but a lot of times it is. So a lot of times, and again, it's not a perfect, that first number that you're using in a dimensional analysis is probably super close to what the probably final guy should end up in terms of significant figures. All right. Any questions on that there? Now, speaking of that, here are some equalities, and obviously some of these you are responsible to know. So we have our basically US or English to English type conversion. So that's an exact conversion. All of these here would be considered exact conversions because they are all basically English to English conversions. These are some of our metric ones, which we talked about. Some of these ones that obviously you should know. These also would be considered exact conversions, because you're basically converting between the same sort of unit scale. Remember that it is metric to English type conversions here that you should look at the significant figures, except for a few that they consider here in this class and they want you to learn, bless you, that are exact conversions. So this one, which you should know, is an exact conversion. They also have, it might be a little different on your notes, but it should be, they want you to learn this number for this one here, 453.6 grams is a pound. And they consider that exact, even though in reality it's really not. There's a few extra digits, but we'll call it exact for this class. And they actually want you to know this one in sort of the opposite version, I think. So I'll just write it here next to it. And that was one I think we wrote earlier, that 1 mile is equal to 1.609 kilometers. And they're calling that exact as well. Again, it's not really exact, but we'll call it exact for our purposes here. So in terms of metric to English conversions that are exact conversions, we'll consider those 3 there as exact conversions. And again, if you come across those in a calculation, you don't have to worry about it. And again, a couple of things. So for example, if we were using this one here, this is a English to metric conversion. So if we did something like, I don't know, we had 32 quarts and we wanted to know how many liters that basically was. So from this equality, we could write 1 liter over 1.06 quarts. Our 1.06 quarts is 1 liter as our conversion factors. Now we're going to start with what was given to us, which is 32 quarts. Once again, it is considered to be sort of on top, even though it's not really written as a fraction. That means, again, our opposite is what we wanted to use. So we want to go opposite location here. And we got 1.06 quarts on the bottom and 1 liter. That's going to cancel out the quarts, and that will give you on your calculator there 32 divided by 1.06. Going to get us this number here, 30.188679. I'll just stop it there. And liters, obviously I have a few more numbers on my calculator. Now, again, liters are the only unit that's left. It's 1 unit by itself up on top, which is what we're looking for. Now, when we go to count significant figures in this case, because we are actually using here a metric to English conversion, we actually have to look at the significant figures in that conversion factor. The one that we look at is the one that's actually a number. So a lot of times one part of the conversion factor will be 1 and the other guy will be a number. So in this case, we would actually look at the significant figures here in this part of the conversion factor, and that's 3. Here we have in our original number 2, and once again, what we did is we multiplied and divided, right? And in this case, our answer should then still end up at 2, right? Because it's still less than what we have in the conversion factor. And we should end up here at 30 liters. Should I write 30 liters like that? I would need a decimal point, right? To make that 0 significant in this case, right? Without it, it would just have 1. So this is the situation if you use any type of metric to English conversion that's not considered exact. And once again, here they consider kind of those 3 exact, even though kind of 2 of the 3 really aren't. But we use the 1 inch is 2.54 centimeters. The 1 mile is equal to 1.609 kilometers exactly, and 453.6 grams is a pound. So again, if you use any of those 3 in a calculation, you don't have to worry about the sig figs, anything else. Again, you do. Again, I would say some common equalities that you should know. This is probably a fairly good table just to kind of know. You'll come across most of the stuff that's on here. A lot of the stuff, hopefully, you know. But I would say definitely in this range, right? These things pop up a lot. Probably the miles and feet do a lot. Clearly, these are our metric sort of conversions that we talked about. So those prefixes will really handle pretty much any of those in that column if you kind of know the prefixes. And really same thing all the way through these guys. If you kind of know the prefixes, you know, you pretty much will kind of get those guys going on. Obviously, we might have talked about before that obviously might not be provided for you. So hopefully you know time as well, minutes, hours, and days. Sometimes people don't. And I would say these are common ones definitely through here. So like I said, pretty much this table is a pretty good one. You know, most of everything on this table does pop up along the way. So I'd probably start this table and for the most part know most of them. I will say probably not too much cups and quarts and pints, but I guess those are good life things to know in case you're baking maybe or something like that. But probably not too much happening here. I would say in chemistry, most of the volume is, you know, this stuff is really, we're definitely the ones that we use most in chemistry. Any questions on any of those? So obviously all these are qualities, and any of these we could write 2 conversion factors for that we could use obviously in dimensional analysis to do some conversions. All right, so just a couple of things here. Again, we have our feet and our miles, gives us our 2 conversion factors. And again, we would use obviously whichever one is appropriate for the calculation. You don't use both because that in the same calculation, otherwise that will undo your calculation basically, right? By the way, if you're doing multiple sort of steps in your calculation, you can get an answer after each step. If you choose to do that, you shouldn't round to the end. So if you kind of want to do it in parts, it's perfectly fine. For me, it's perfectly fine. Some teachers want you to do it all in one step. I don't really care. You can do it in parts if you want. But if you do get an answer, try not to round to the very end. Otherwise, you'll have some rounding error that will happen. Obviously, we sometimes get conversion factors in words. So 65 mph is miles per hour. So whenever you have something per something, that's basically 2 units together as a fraction. The number stays with the first unit. So 65 miles per hour means, frankly, you are driving 65 miles in 1 hour. If you kept that speed the whole time, you would go 65 miles in that 1 hour, or you could go in an hour 65 miles. So again, the number goes with the first unit, and the second unit on the bottom in the fraction is usually 1 when you have multiple units. Again, we want to set it up this way where you could clearly see where these things are. It is a really common error that students make a lot when they kind of don't set it up that way. They just very commonly multiply when they should divide or divide when they shouldn't. 91 octane, 305. See how old that slide was. By the way, that was super expensive when I made that slide, 305. It was very much expensive amount. But that basically means for every gallon of gas you get there, you pay 305. Yeah, I'll take it. And 305 over 1 gallon in that case. Now, percentages is also something that we get a lot of in terms of sort of words that we do want to turn into usable sort of conversion factors. So whenever you have a percentage, really the easiest way to turn it into a usable conversion factor is to assume that you have 100 of it. And the purpose of that is it pretty much just keeps the numbers the same, right? So you got like 80% on your exam, that probably means you got 80 points out of 100, right? So it just kind of keeps the numbers the same along the way. So if you have somebody that had 12% body fat by mass, you could do more of the metric approach to that. That would mean somebody has about 12 kilograms of body fat per 100 kilograms of body mass. And that would give you your two conversions that you could use. Want to go more of a US sort of measurement, that means you got 12 pounds of body fat for every 100 pounds of body mass. And again, we get our sort of two conversion factors that we can use. So a lot of times, if you're given a percentage in a problem, it's really helpful just to convert it into a conversion factor, take a more dimensional analysis approach. And like I said before, a lot of times when we get to certain calculations, if you just kind of think of it in a dimensional analysis approach and a unit approach, a lot of times it will kind of do the formula for you, like I mentioned before, without you having to go, okay, I got to rearrange this formula to kind of solve for something. So if you kind of do that, it will sort of do that calculation for you a lot of times. All right, so we sort of talked about, obviously jumped into dimensional analysis already, but again, that is what they want you to show work and how to show work. Here are, in general, the general steps to follow when you're doing a dimensional analysis problem. A lot of times you want to write what's given to you in the problem. You also want to write what you want to find. You want to think about a pathway to get to your end result. Now, when you're doing sort of conversion problems or these type of problems, there could be multiple sort of pathways to get to the right answer, depending on sort of what conversion factors you choose to get there. You could go some different routes, and they all really should kind of get you to the same answer if you choose legitimate conversion factors. You want to set up the problem where you can see the units canceling. Obviously, you want to solve the problem for the correct number of significant figures. Once again, when you're doing this type of math, it's pretty much all multiplying and dividing. So that is all against sig figs, smallest number of sig figs. And the only one you have to worry about again is if you come across a metric to English conversion factor, you need to take a moment and see if it's one of those three that are exact. If it is, then you don't have to worry about the sig figs. But if it's not one of those three, then you do need to take those guys into account, the significant figures. All right, so obviously here we had how many pennies is in $3, kind of similar to one we did earlier. So I'm just going to kind of go through this one here. And we'll take a look at this one. Why don't we try this one here? All right, you go to the AM PM and you get a 32 fluid ounce drink of Diet Coke from the Thirst Oasis. Crushed ice, cubed ice, your choice, I guess, right? We want to know how many gallons of Diet Coke is that. So set it up using dimensional analysis. Here are a couple of equalities that might be helpful and see what you get. Okay, so let's take a look. So once again, we are starting with 32 fluid ounces. We want to get to gallons. So we can find some equalities that will allow us to do that. We have fluid ounces. We can use fluid ounces to get to quarts. Once we have quarts, we can then could get it to gallons. So that's sort of the pathway that we want to kind of choose to get us there. Obviously, from these equalities, you could have two conversion factors for each. So if you wrote those out, it would look something like this. So we're going to start our calculation with 32 fluid ounces. Once again, it is basically by itself, which means that those fluid ounces are up on top. So once again, all you have to remember in this case is just opposites to get rid of it. So we want it where the fluid ounces are on the bottom. So that's going to be that conversion factor right there. That would give us 1 quart is 32 fluid ounces. If I were to stop the calculation right at this point, the fluid ounces on top and bottom would divide themselves out and cancel, basically equal 1. That will leave me quarts at this point. Now I could clearly see quarts are on top and I don't want them. So again, to get rid of them, we're going to go opposite. So we need the conversion factor where the quarts are on the bottom. And in this case, that's our guy here on the right is going to do that. So we can continue on with the calculation. And 4 quarts on the bottom, 1 gallon up on top. Quart on top and bottom will once again cancel each other out. And we are left with the only unit that's left, which is gallons, and it's on top, which is good because, again, if you're solving for 1 unit, it needs to be on top when it's all said and done by itself. So once again, we're going to multiply by whatever's on top. We're going to come back here and divide by what's on the bottom. And in this case, basically, there's not much to multiply up on top since they're all ones. So we basically have 32 up on top. We're going to divide it by 32. By the way, hit equals, and then divide it by 4 and hit equals. Yeah. And that gives us 0.25 here gallons. And in terms of our significant figures, really, we got an exact number here. That's conversion factor, exact number there, so we don't have to worry about it. Once again, this is the only one that we have to worry about, which is our original number that has 2 significant figures, and that ends up with 2 significant figures on our answer in this particular case. The answer is 0.25. The answer, by the way, is not 1 divided by 4 because it makes me think you're too lazy to punch that into your calculator. Yeah, so don't do that. Don't leave an answer as a fraction. So make sure that you divide it out. It's not bad in that sense, but I have had people write something like for an answer of 455 miles over 3,280, hours, and just circle it. Yeah, so don't leave it as a fraction. Kind of divide it out there at the end. Any questions on that setup there? Once again, you don't need to necessarily show everything that's on the page here for full credit. Basically, the bottom there is what you need to show to get full credit. Yeah. Any questions on that one? All right, let's try maybe another one here. An antibiotic doses of 500 milligrams is ordered if the antibiotic is supplied in liquid form of 250 milligrams in 5 milliliters. How many milliliters will be given? Sometimes happens as well. Sometimes you're given information in the actual problem, which frankly you could use as a conversion factor. And that is the case here. We're basically told our medicine here is coming in 250 milligrams per 5 milliliters. That's really specific for this particular problem, right? And that can be used really as a conversion factor. So sometimes we are given sort of conversion factors in the problem. You could actually, if you wanted to flip this around the other way and use it as a conversion factor. So we are going to start with the 500 milligrams. Once again, we want to get rid of milligrams. We are going to use what they gave us basically as a conversion factor in the problem. And same thing, we're going to go opposites, which means we do need to kind of flip it around and use it in the opposite direction there. And that's going to give us 5 milliliters on top. Opposite location there for milligrams on the bottom. They will cancel. We are again going to multiply and divide basically. Yeah. So we're going to go 500 times 5 and divide it by 250. And that's going to give us 10. Whoop, come here. It's going to give us 10 milliliters, right? Now we want to think about significant figures. Do we have to look at the significant figures here? We actually do, because again, it's not a real sort of equality, if you will. It's just, again, specific for this. So we do have to take into account. We actually have a couple numbers we actually look at in this case, right? They both actually have 2 significant figures, basically, right? And our original number here has 3 significant figures, right? So our answer should actually end up with 2 significant figures, right? I can't leave my 10 like that, right? Because that only has 1 significant figure. So I can put my little decimal point there, and now we'll have 2. Should I add a 0 at the end of it? I should not, because then it will have 3, right? So again, remember, just adding zeros is not always, the right thing to do as well. Any questions on that? So a lot of times you are given sort of conversion factors in the problem. In those cases, you should look at the significant figures sort of involved with those guys when you're kind of taking into account where your answer should be. In this particular case, it actually is the one that determines how much our answer should end up at. Any questions on that? Yeah. Again, really just all of that, yeah, without the arrows and stuff, but all that part, yeah. So really, to get full credit, you need to show the setup showing dimensional analysis, which is kind of what we're doing there with the units. The units need to be on everything. You need to have the answer with the correct number of significant figures and the correct units. Again, if it helps you to do all the other stuff, like, right, what you're trying to find, and the conversion factors, do that, but you don't necessarily have to do that for full credit or anything like that. But definitely what's in the box there, outside the arrows to say multiply and divide, you need to, show that, yeah. Other questions? Okay. All right, during surgery, patient gets 5 pints. How many milliliters of plasma was given? Here are some equalities that might be helpful. Again, here we got 5 pints. We eventually want to get to milliliters. So this is one pathway, pints to quarts, quarts to milliliters. Once again, our conversion factors there for each of those equalities. Here we're going to start again with our 5 pints. And at this point, we want to go opposite. So we're going to go with where pints there are on the bottom. So 2 pints is 1 quart. At this point, our pints will cancel. We could clearly see quarts are up on top, which is going to make our decision pretty easy because we need to go opposite to get rid of it. So we just pick the one that has it in the opposite location. And again, we're going to set it up that way so that we can see it. That will mean that our quarts here will cancel. That's going to leave milliliters as really the only unit that is left. We're going to multiply across the top here. And we're going to end up with 5 times 946 divided by 2, basically. And that's going to give us 2365 on our calculator milliliters. So now we need to think about what we need to look at. I believe this is a kind of English to metric conversion, which means we should look at the significant figures here, right? And that is going to be 3 for the 946. Here we don't have to worry about it because it's the same. So this is exact. Here we have 2. So our answer should end up with 2 significant figures there. That means we should end up with maybe something like 2400 milliliters as we go to the proper number of significant figures. You also could do a little scientific notation if you wanted to as well. 2.4 times 10 to the 3 as well. You could have done that as well. Any questions on that particular one there? All right, one last little conversion type problem here. All right, you're stranded 125 miles away from home. You decide you have no money. Why not? It seems like a nice day. Let's take a walk. And you decide to walk home. You walk at an average 55 feet per minute. How many days is it going to take you to get home? Right, you don't stop. Let's keep going. Keep trucking like the Energizer Bunny. And maybe some equalities that will be helpful. Okay, so let's take a look. So in this case, we have 125 miles. We're also given how fast we're walking, which we can use as a conversion factor from the actual problem, and we can flip it around if we like. That is really a rate here, and that's going to allow us to go from our distance to time, which is ultimately what we're looking for. The problem that we do have, though, is this length distance or distance is in miles. This one's in feet, which means they're not going to work great together. So you have to do some type of conversion. You could either convert the miles to feet, or you could do the feet one to miles. Whichever way you want to do it, it will work. I'm personally going to convert the miles into feet and then just use the feet per minute like it is, and then everything will work out first. So that's really what I'm going to do first. I'm going to take 125 miles. I'm still just going to do dimensional analysis on it. So I want to get rid of miles. I'm going to use this conversion factor, or really equality, to do that. Again, we want to go opposite to cancel. So on the bottom should go 1 mile. Up on top should go 5,280 feet. Our miles here will cancel, and we will end up with 125 times 5280, about 660,000 feet. You'll definitely get your steps in today. All right, there we go. You got your 660,000 feet in this case. Now I have it in feet, which is going to work really well with our sort of rate here to get it into time as a conversion factor. So we're going to go with 660,000 feet. Once again, we're going opposites to cancel. That means I actually do need to flip it around and have the feet on the bottom. So that's going to give me 55 feet per minute. The feet here will cancel. I'm now in units of minutes, but I do need to get that into days. So I could then go, if I like, minutes to hours. So once again, using this equality here, opposites. So minutes are up on top. So we do need to put the 60 minutes on the bottom, which means we're dividing by the 60 in this case. And those minutes will cancel. If I stop at this point, I'm in hours, which is close to what I want. So I just now need to take it from hours to days. And again, there's 24 hours in a day. Because I set it up like this, I could again clearly see my hours are up on top. So to get rid of it, we're going to go opposite location, which means the hours do need to go on the bottom and the day needs to end up there up on top. Once again, here we're going to multiply across the top, which in this particular case is pretty much nothing to multiply. So we're going to then divide by 55. By the way, hit equals. Divide by 60, hit equals. And divide by 24 and hit equals. And if you do all that good stuff there, 8.333, a bunch of threes, and days we will have in this case. First off, any question on the setup here? So significant figure wise, we want to figure out what's going on. We don't have to worry about that. Obviously, that's an exact conversion, right? We don't have to worry about that one. That's an exact conversion. We do have to worry about this one, right? The 55, which has 3 significant figures, right? We do have to worry about the original number, right? But that original number actually came from this number, which has how many significant figures? 3, right? Even though technically I didn't write 3 significant figures here, this one should still have technically 3 significant figures, which means my answer actually should end up with 3 significant figures in this case, right? 8.33 days. Again, I didn't round or anything like that. I didn't write it in scientific notation, but that really should have 3 significant figures. Any questions on conversions, how to set them up? Obviously, this is the way you need to show your work to get full credit. All good. All right, then let's talk a little bit about the second experiment we're going to do today, which involves density. Let's talk a little bit about density. The density of an object is basically the amount of matter that's present per volume. There's really 2 types of common units that we'll come across in this class for density. Grams per milliliter or grams per cubic centimeter. And those are common units of densities really for solids and liquids. We don't really deal with it too much here, but with gases, grams per liter is oftentimes the unit of density for gases. When you take 1A, you'll deal with that. But for us, pretty much these are going to be kind of your main units that we see. Remember, again, as we talked about, 1 milliliter is the same as 1 cubic centimeter. So it is a 1-to-1 conversion between them. The density of an object determines, for example, whether or not a substance will sink or float in, say, something like water. If something is more dense than water, it will sink. If it's less dense than water, it will float. The density of liquid water, which, by the way, the density does change with temperature, they want you to use, I believe, 1 gram per milliliter. So again, that is something that you should know. The density of liquid water is 1 gram per milliliter. It really does change with temperature. So we'll go with this as the density that you do need to know. By the way, if you take like some Diet Coke can and a regular Coke can and pop it into a bucket of water, will they both sink? Will they both float? One sink, one float? Actually, one will sink and one will float. Which one will sink? The regular Coke. Yeah, it has a lot of sugar in it, so it will sink. Diet Coke has artificial sweeteners, so it actually will float. It's a good party trick in case you need one this weekend. It is Labor Day, I think. There you go. So when we talk about density, there is the formula for density, which is the density is equal to the mass divided by the volume. And that is a formula that you do need to know. So D is equal to M divided by V. And if you want to rearrange it, the volume would equal mass divided by density. You would multiply the volume to both sides and divide the density. If you want mass is equal to volume times density. Sometimes people remember this through our favorite place to go, the DMV, yeah. The DMV triangle, yeah. Density is mass divided by volume. volume is mass divided by density, and mass is volume times density. So sometimes that's the way people remember it. So you obviously can plug and chug into here. If you have the density of an object, like for example, water's density is 1 gram per milliliter, you can use that as a conversion factor. You can flip it around. And like we were talking about a second ago, you could kind of do almost like a dimensional analysis type of calculation with the density, and you might not have to worry about rearranging the equation. Just canceling out the units will kind of do it for you. Any questions about there? I want to try one here. A block has a volume of 25.3 cubic centimeters. Its mass is 21.7 grams. What is the density of this? We're dealing with density, which is mass divided by volume. Obviously, cubic centimeters is our volume. And 21.7 grams is our mass. So in this case, we actually have everything that we need. So we could just plug and chug into this guy here, 21.7 grams divided by 25.3 cubic centimeters. That's going to get us here 21.7 divided by 25.3. Guess it would help to actually put the whole number in there. There we go. Going to give us on our calculator 0.8577071. The units are grams per cubic centimeter, as they do not cancel. We do need to look at significant figures here, right? We're dividing. Top number has 3, bottom number has 3, which means we should end up right about there. So 0.858 grams per cubic centimeter. Yeah, would be our answer. Again, the units do not cancel, so you got to keep both units. Number stays with the top number stays with top unit. Bottom one is 1, basically. Question on that one there. Now let's talk about something that is important in terms of how we get volume. So up until this point, we talked about really 2 ways to get volume. You can obviously get the volume of an object by just simply reading it, right? Taking a reading. You could get the volume of a solid by going length times width times height. Again, each of those sort of measured with like a ruler in centimeters, giving you cubic centimeters, which is a volume. The third very common way that you could get a volume is what is known as volume by displacement, which we'll also do in the lab today. And that is if you have a certain amount of, say, water or liquid in a container, and you put in a solid object into it, that solid object will displace a volume that's equal to its own volume, which means you'll see the water level rise. So if you take the difference in the volume between where it started and where it ended, it will give you the volume of an object. So very common, like you're going to do today, you will take like a graduated cylinder, you'll fill it up with some water, you'll take an initial volume reading, you'll take a solid object and put it in. It will cause the liquid level there in your graduated cylinder to rise to a final volume. And again, if you take the difference between those two, the volume of the object will equal the final volume minus the initial volume. So that is a very common way in density to figure out the volume of an object. You just simply toss it in some water and take a volume reading before, volume reading after, subtract the two, and that will give you your volume. Question on that there.